Hi, this video is to help you understand how to calculate the heat of a chemical reaction from the bond energies that are provided. Remember, bond energy is the amount of energy required to break a chemical bond. It is also the amount of energy that is released when that same chemical bond is formed. The two numbers are exactly equal. It just depends if you're putting heat into or out of the system. Now, a typical question might look something like this that says, calculate the delta H, which is the change in enthalpy. All right, change in enthalpy in kilojoules per mole for the burning of nonane. Now, nonane happens to be right here. This is the combustion of it, and an unbalanced chemical equation is provided. Now, our first step is we need to balance the equation. All right, so we do that like we normally do. We have carbon, hydrogen, and oxygen. We have 9, 20, and 2. On this side, we have 1, 2, and 3. So in balancing this, we have that, and then we use our coefficients in order to make the numbers the same. I got 9 carbons on the left. I need 9 on the right. So I'm going to put a 9 in front of the CO2. That makes that a 9. That also changes the amount of oxygens. So 9 times 2 is 18 plus 1 gives me 19. Over here, I have 20 and 2. So I need to put a 10 in front of the H2O. 10 times 2 gives me 20. Total number of oxygens now is 9 times 2 is 18 plus 10 more, 28. And then I finish off by saying, well, half of 28 is 14. So I put a 14 in front of there, and voila, it is now balanced. Now the next step is to create the Lewis structures for each of these. All right. So the Lewis structure for the hardest one is this guy right here, C9H20. Well, remember, carbon has 4 valence electrons, so it can make 4 bonds. And basically, the way this works is you have 9 carbons. So I'm going to line up 9 carbons in a row. Each one is going to be bonded to each other. All right. And then the 20 hydrogens come and they attach at all the other locations. Since each carbon must make 4 bonds, each carbon has two hydrogens plus the 2 ends have an additional hydrogen. So to draw it all out, and don't worry, on the test you're going to have smaller molecules than this, but I wanted to use this to show you, just how difficult it could become. So you have all of that, all right? And then you have oxygens. So you have oxygen, which has 6 valence electrons. Again, I get that by looking at the periodic table. Oxygen is in column 16, so it has 6 valence electrons. So 1, 2, 3, 4, 5, 6. And I put the second oxygen, since it's O2. 1, 2, 3, 4, 5, 6. I combine, and I have a double bonded there. Now, since I have 14 of them, that means I'm going to have this OO double bond. That's going to be times 14, whatever number I find for that. And then that's the reactants. For the products, CO2, I have carbon, makes 4 bonds. I put an oxygen next to it, 1, 2, 3, 4, 5, 6. I make a bond there and a bond there. Another oxygen, 1, 2, 3, 4, 5, 6. And I make a bond there and a bond there. Again, technically, we shouldn't have these extended ones. So we make a double bond and a double bond. Just like here, technically, erase all those and it makes a double bond between there. So here we have O and C double bond, O and C double bond. And keep in mind that we got 9 of those. So we're going to have to multiply that by 9. And then finally we have water, which is the simplest of them. You have oxygen 1, 2, 3, 4, 5, 6, and we attach 2 hydrogens to them. And that one is going to be times 10. Now, when we're looking at the bonds, we use for the bond energy this chart here. And I know it's a little hard to read, but you guys will have one that you can see a little bit better. But basically, it goes and gives all of the bond energies for pretty much every single bond that you can expect to find in a normal class. For example, down here, it has C double bonded O is 745. Don't worry about the length. All we're doing is the energy in kilojoules per mole. So C is 745, all right? Except you notice down here, it says that the C double bonded O bond energy for CO2 is 799. So basically, these bonds down here, the 2 bonds here, each one is 799. All right. So basically, I have those being 799. So I'm using this chart to figure out what the bond energies of each one are. So the easy way of keeping track of all this is, first of all, I take my reactants. I see that I have some carbon-carbon bonds and I have carbon-hydrogen bonds. So I'm going to do those separately. First of all, the carbon-hydrogen bonds. There are 20 of those bonds. I go and I count, and there's 20 of them. So I go 20 times how many, the actual bond energy. And according to my chart, the hydrogen-carbon bond, let me find that, hydrogen-carbon bond, it's on here, I know it is. Hydrogen-carbon bond, where did it go? There it is. It's 413, okay? So the CH bond is 413 kilojoules per mole. All right? And I have 20 of them. I'm going to multiply those out. All right? And since that's energy going in to break those are all positive numbers. And then I have the OO bond. Again, these are the reactants on the left side. So I have the OO double bond, and according to my chart, so the OO double bond, I have 14 of them. So 14 times the OO double bond is 495. And then I'll multiply that. So I'm going to do that right now using my calculator. And I'm going to go 20 times 413 equals, all right, and I get 8,260. And then I go 14 times 495 equals 6,930. All right, so those guys are going to be positive since that's the energy going into the system to break those bonds. These bonds are all going to be negative because these are the energy that is released when those bonds are formed. Now, with CO2 here, each bond is 799. But if you notice, I have 2 of those bonds per molecule. And I have 9 molecules, again, based upon my balanced chemical equation. So basically, I have 9 times 2. I have for the CO double bond, I have 9 times 2. I have 18 of those bonds. And I'm going to multiply. And since this is an exothermic reaction to form the bonds releases it, that's negative 799 kilojoules. And on my calculator, 18 times negative 799 equals, I get 14,382 negative. And then finally, for the water, I have 2 HO bonds per molecule times 10. So that's going to be 20 of those bonds. 2 times 10 is 20, times the HO bond energy, which according to my, let's see, OH is negative 467. And again, on here, so I want to make sure you guys got this. Right here, the OH bond is 467. That's where I found it. And I'm saying it's negative because I know it's a product, and the product's bonds give off energy, so that's a negative number. So I go 20 times negative 467 equals, and that is negative 9340. Now, to find the total amount of energy for this reaction, okay, it is, I simply add up the entire thing. So I take negative 340 plus negative, all right, plus negative, 14,382, and that's negative. So plus positive 6930 plus 8260 equals. And I get a grand total of negative 8,532. That is in kilojoules per mole. And that is how you calculate the delta H, or change in enthalpy, for a chemical reaction using bond energies. I hope you found this useful. If you have any more questions, please talk to me during tutorial. Thank you.